Hi, this is Professor Stugard, and in this video we're going to discuss how do we use data. So our goals for this video, first of all, just to understand the different ways that data are used, and to learn how those ways might be different, but they also complement each other and kind of work together. So there's two main reasons that we're going to collect data. The first is we want to know what's going on right now. And the second reason is we want to use that data to help us make predictions about what's going to occur in the future. And in both cases, it's really about money. This data is valuable. Hopefully you can imagine that if you run a business, you want to know what's going on right now. You want to know what you have in inventory, how much you're making right now in revenue and profits. And then also you want to make predictions about what's going to happen in the future, especially if you change some variables about what's going on. And that makes data very, very valuable. And that's one of the reasons that statistics and data science are now kind of the kings of mathematics, having dethroned calculus. So let's talk about how we collect data. Because when we collect data, we're trying to get a snapshot about the world around us right now. And typically when I try to collect that data, I can't gather every single piece of data about whatever it is we're studying. That's just not really feasible, so we collect just a small sample of all that available data. This sample is referred to as our point estimate. Now, point because we're talking about this one specific point in time. Now, for example, Gallup, the polling organization, conducted another poll this past May asking whether or not people believe that same-sex marriage should be valid under the law. Now, out of the 1,003 people polled, 683 of them were in favor of same-sex marriage being recognized as valid by the law. This is an example of descriptive statistics. Descriptive statistics is literally just saying exactly what it is we collected and what the results were. So descriptive statistics would state that 683 of the 1,003 people polled this year support same-sex marriage. That's it. Now, when we talk about that point estimate, obviously point, like I said, is that one specific point in time, but then the other word is the estimate. And it's just an estimate because if I took a different sample, that might give me a different estimate. I might get a different set of data. If I asked another 1,003 people, I wouldn't expect exactly 683 of them to tell me that they support same-sex marriage. I would expect probably a different value because, again, just the randomness of collecting data and asking people. So if I know that if I asked a different sample of people the same question on the same day and I wouldn't expect the same results, how can I actually use statistics? There's this variability, there's this randomness. So how can I be sure that my sample is going to accurately reflect everyone? Well, we can't. Even the best designed studies, even if we go out of our way to make sure that we are not including any bias, that we are trying to get a representative sample of everyone, yeah, randomness happens. I'm only asking 1,000 people. If I'm talking about all Americans, there's over 300 million Americans, over 200 million adults that would have an opinion about this topic. I can't ask everybody. And if I ask a different group of 1,000 people, I'm going to get a different answer. And so does this mean we're stuck? Well, no. This is where inference comes in. Statistical inference is now when we combine that sample that we took, that point estimate, with known facts about probability and our probability distributions, and that gives us a level of confidence and a margin of error for our range of possible values. This is called inference because from our point estimate, we're going to infer how the population at large probably feels about whatever it is we're asking or whatever it is we're trying to collect our data about. So, going back to the same example, of that 1,003 people polled, 683 are in favor of same-sex marriage. So this becomes our ratio. We can find the proportion of people. And if I divide those two numbers, I get 0.68 or 68%. So I can take that 68%. And again, I know that there's some variability. So I do my inference. I find my margin of error. My margin of error is 0.029, or I'm going to round to 3%. I rounded to 68% too, just to make it kind of even numbers. This is going to be covered in a different video. This is outside the scope of this video, how I calculated that margin of error. It's this process called inference. But that margin of error means we take our point estimate, 68%, and we say, well, we could probably go one way or the other. Let's give ourselves a range of possible values that percentage probably falls in. So inferential statistics would state that with 95% confidence, the current percentage of Americans in favor is somewhere between 65% and 71%. So now we give ourselves a range of values, because if I asked a different group, I'd give it a different value. But again, we're going to assume that we did a good job collecting our data. So we're going to say it's probably somewhere around what we actually collected. Now, whenever you see that phrase with 95%, you should really just kind of replace that in your head with the word probably. Probably the current percentage of Americans in favor is somewhere between 65 and 71%. Is it for sure? We don't know. We'll never know. But based on our available data, that is our best guess. Now, again, that's all telling us about what's going on right now. What if I want to predict the future? Well, before we get to that, I just want to reiterate this difference. Descriptive statistics describes exactly what it is we have collected. 683 of the 1,003 people polled support same-sex marriage. Inferential statistics is when we include some wiggle room. We include a margin of error. We give ourselves a range of values that the true percentage, that true parameter probably lies in. So now, how do I predict the future? Well, we're going to need more data. And as I said, Gallup polled again. Gallup has been polling Americans on this question about support for same-sex marriage since 1996. And so this is from a publication they put out in 2021. So it didn't include the newest data, but that's okay. And you can kind of see that way back in 1996, which is just about 30 years ago, only 27%, only about a quarter of the country supported same-sex marriage. We can see that as time progressed, that percentage has gone up and up and up and has even peaked at, well, looks about 70%. So can I make a prediction about what's going to happen in the future now that I have my data about the past? And how would I do that? Well, let's say I want to predict how much support is there going to be in another 25 years. In the year 2050, how much support will there be for same-sex marriage being recognized as valid under the law? Well, we want to find the patterns, and we have to be able to represent these patterns mathematically. And that's the important part, but it's also kind of interesting because we can come up with lots of clever ways to represent those patterns. We can describe the data in lots of different ways. But the mathematic part of this is that each of those ways that we represent these patterns and then try to come up with a way to make predictions, we're all going to be using algorithms. And algorithms are like a set of steps that we can follow in each particular instance to come up with some sort of prediction machine that we want to be able to use. Now, in this case, we want to predict a value. I want to predict the percentage of Americans who would be in support. That's a number, that is a value, which means I want to do regression analysis. And the simplest type of regression analysis is going to be linear regression. Now, this is where we use the least squares algorithm on the data to create a line of best fit, which is going to minimize the distance of each point to the line that we're creating. And again, we're going to go more in depth in different videos. I just want to give kind of an overview here. So again, all of this will be described in greater detail in other videos. But this is actually an example of machine learning, where a machine can learn this pattern from the data based upon our mathematical algorithm that we've come up with as humans, and with no other input besides telling the computer, here's your data, here's your algorithm, put them together. And the machine can learn the patterns in that way. So I took that data, I exported it to Excel because that's a great way to investigate data, is through Microsoft Excel. And I found my line of best fit. And so here's the line of best fit. And hopefully you can see here that that does seem to model the data pretty well. Most of the data points are pretty close to that line. Maybe there's a little that are off here and there, but for the most part, it seems to match pretty darn well. That line is, well, given by this, which is just our y equals mx plus b form. So it's just that simple kind of, algebra 1 stuff. And that is machine learning. It came up with this line that is going to let me predict the future. Y equals 1.6842x. So That 1.6842 becomes my m, or my slope, and then my y-intercept is negative 3,334.9. So for this line, again, the way I set up my horizontal and vertical axis, x is the year, right? That's my horizontal. The percentage is my y-axis, so y is my percentage. So to predict for the year 2050, once I have my model, I just need to now plug in the year. So I'm going to substitute x equals 2050 for the year 2050. I plug that in, order of operations, multiply first, subtract second, and I get the value 117.71. So in the year 2050, we predict that 118% of the population will support same-sex marriage. Oh, wait a second. Can we have 118% of the population do anything? Well, no, because 100% is everybody. You can't have more than 100%. And even then, does it seem likely that you will get 100% of every single person to agree on one thing? No, that's never going to happen either. There are so many different opinions and perspectives and experiences that you will never find everybody that agrees with anything. And social media is very good at exploiting that and finding someone that you disagree with, and they only need to find one of them, and they'll make you think that it exists as a larger segment of the population. And you get angry and frustrated, and, well, that's okay. Well, not really. But that's the way the world works. So, what happened here? Does that mean that that line that looked like it was really good, it was really close to my dots, actually didn't work? Well, if I extend this out, and I kind of extend this, and I look, and I go all the way to 2050, well, the most that can happen is 100%. I can't get more than 100%, and we can see that that's going to happen somewhere around 2040, maybe 2039. And so, no, this model is not going to work for that far into the future. And it is very, very important to remember that there are limitations with any type of prediction. Machine learning is incredibly powerful. It's been used with great success across many different areas and disciplines. It helps us make predictions that humans could not do alone. It helps give us a great guide to help make predictions based on our data. However, we need to remember that we still need to use our human intuition to interpret these predictions and to make sure that our model actually makes sense in context. Now, that's not always the case. This article was actually published by ABC News back in 2008, and by ABC News, the study predicts that the obesity apocalypse will occur by the year 2030. Will nearly all Americans be obese by 2030? Diet experts have their say. And yeah, this really appeared on ABC News, and the article goes on to state that they use a linear regression model, and based on that linear regression model, it says even more troubling. The authors note that by 2048, all American adults would become overweight or obese. Does that sound reasonable? All American adults, every single one, 100%, everyone's going to just become obese and overweight? No, that's ridiculous. And someone like ABC News should know a heck of a lot better than that, than to write an article and publish it that states something as ridiculous as that. And the shame is, being overweight and being obese, those are serious health concerns. One of the number one killers in this country is heart disease. Diabetes is an issue. Cholesterol. All these things are making people very unhealthy and shortening lifespans, and it is something that we should be paying attention to, and something that we should absolutely be looking into and trying to prevent. But when you publish things that are clearly ridiculous like this, I think you're probably hurting your case more than anything else. Anyway, this is how machine learning works, though. Machine learning algorithms are used to predict individual behaviors. They can classify objects, predict values. They can do a bunch of tasks. And although we implement that machine learning in different ways, we use different algorithms, we create different types of models, the general process, though, is always going to be kind of the same when we want to predict the future. We need to gather data. We need to find patterns in that data, describe them mathematically, and then we use a machine learning algorithm to help us create that model. And that model, we can almost think of like a computer program. We train our model using that data, and then we can use that computer program and kind of ask it questions to help us figure out what might or might not happen in the future. And again, once that model is built, we have to make those predictions by plugging new data, and the model is going to output whatever it's going to output. The computer, well, it's going to do exactly what you want it to do, not necessarily, it's going to do exactly what you tell it to do, not what you want it to do. And it's important to recognize that you need to always step back and ask yourself, hey, is this a reasonable prediction? So, to reiterate, we have our data, we apply an algorithm, that builds us a model. We can then use that model for predictions. And linear regression is just a really easy one, and something that we can take a look at in a basic stats class or a machine learning class, because it is that powerful and that important. It's just also important that we remember the context of our data and where it's still going to make sense and be a valid model. So, just like we performed inference to include a level of uncertainty about our point estimate, it's important to test our model too. And our model might have limitations that only make it useful to describe either the exact data set that we've actually used or maybe just very close to that. And it might not make accurate predictions about the future. You're not going to know that unless you test it. So whether you're doing a point estimate and you want to include wiggle room to make sure, hey, could be different. We don't know. We want to make sure we're very clear and upfront about that. The same thing with our model. We want to test it. We want to make sure that, hey, this is going to behave the way I expect it to, given different types of data. So, to summarize, there's two main reasons data is collected. One, we want to know what's going on right now, which means we gather data, create a point estimate with inference. Or I want to make predictions about the future, where we gather data, build a model, and we hope that that model captures our pattern in the data, and then we can use that model to make predictions and test its validity. All right. So I hope we cleared some things up about how we use data today. And as always, take care of yourselves.